Thank you very much for having me. It's a pleasure to be here. For those of you who heard my talk a couple weeks ago, there'll obviously be some sort of similar themes, but I think there's some people here who weren't there, and of course I'm going to go into a bit more detail. So, all right, so let's start with some motivation. So let's fix a prime L. And then, so our motivation comes from this theorem, the modularity theorem, which says that if we have E elliptic curve over Q, there's many ways of stating this. It'll be most convenient to formulate it this way. Then there exists a modular form F such that there's association, so that there's an isomorphism between the Galois representation attached to F and the Galois representation attached to the elliptic curve. So this is p-adic on the Tate modular elliptic curve representations. And of course, this is the theorem of Wiles, Taylor-Wiles, and Breuil, Conrad, Diamond, Taylor. And so our motivation is going to be talk a little bit more about sort of what some of the main results that go into this theorem. So one main component in a technique introduced by Wiles that goes into this theorem is known as modularity lifting. So I want to say not a specific modularity lifting theorem, but just sort of what a modularity lifting theorem looks like. What the idea is, so I'm going to say this is a sort of prototype for a modularity lifting theorem, which says that, so now if you give me a p-adic Galois representation of, say, let's just say the Galois group, absolute Galois group of Q, GL2 QL bar. And let's say that its reduction, this is rho mod L, is, let's just say, irreducible and modular. So, and if furthermore, rho then has some other properties, which I'll just say it's nice. For example, if rho, for example, comes from an elliptic curve, comes from geometry, then that's a certainly very nice representation. And then the conclusion is that rho is modular. So the idea then is to lift the modularity of this complicated p-adic representation from this modularity of this rho bar, which is somehow a much simpler object. All right, so the key tool here then, what this falls under is sort of Galois deformation theory. So the idea is we're going to study all deformations of rho bar, and then maybe the sort of intuitive idea is that we want to sort of pick out the ones that come from modular forms. And so what's one way that we pick out nice, sort of using this sort of nice condition? One way we pick out things that come from modular forms is using local conditions. And so that's, so we're going to impose, so we have this global Galois representation, and we can impose conditions on the decomposition group for each prime p. OK, so let's just move right to the local situation. So let's take K to be a finite extension of QP. And then I'm going to fix a residual representation of the Galois group. This is Galois group, the absolute Galois group of K. And then let's just go ahead and work with GLN. And FL, or it could be some finite extension. Doesn't matter. So recall then that the deformation, so the sort of, to formalize this Galois deformations, so the deformations of rho bar then is it assigns to any Artin local ring with residue field. So this is just really just the residue field FL, the set of lifts of rho bar. So this is the set of rho continuous representations. So this, this is a functor from Artin local rings to sets, and assigns to any A the set of lifts rho from into GLN of A. So this is the frame deformation ring, but since I'll just always be working with the frame deformation ring for it, and so I'm just going to drop the box, and I'll just talk about this, since it doesn't really matter. It just simplifies things. All right, so examples, of course, are just sort of like z mod L to the nz. So you can sort of lift that way, or you could think of like the dual numbers over FL. So you sort of like horizontal deformations as well. And so the great thing about this is that this deformation functor has some geometric content to it. So it's d rho bar is represented, by some power series ring. Some quotient of a power series ring, say x to the d on I, together with the universal lift into GLN of R bar. D has no particular significance here, so this is our sort of universal family. And a local condition then is going to be a sort of closed condition on this space. So a local condition, to be precise, what I want to give you is some subset of the set of lifts, so some subfunctor of d rho bar, which is represented by a quotient of R rho bar. Okay. So two examples. First one is just we could take the unramified guys. So this is unramified lifts. Another example, what you might call like sort of ordinary, is the upper triangular lifts. So of course these conditions are only really meaningful if the original rho bar satisfies that property, is unramified or upper triangular. And so what we're going to focus on for the rest of the talk is maybe the most subtle local conditions. And the most subtle local conditions occur when we take L equal to P. So when we're looking at p-adic representations of the local Galois group of a p-adic field. So some brief sort of motivation for why things get so let's go back to our elliptic curve. So now let's say we had an elliptic curve over QP, for example. And let's look at the L-adic Tate module as an action of the Galois group of QP. Then if P is not equal to L, then we have this nice criterion which says that this Galois representation is unramified if and only if E has good reduction. So in particular, the geometry of E is then reflected in this sort of unramified condition on the Galois representation. So when L equals P, or P equals L, then this L-adic representation is always ramified. And the equivalent condition, the sort of unramified condition, becomes this more subtle condition in p-adic Hodge theory called the crystalline condition. Oh, we're still we can. So if we want a local condition that captures the geometry in the same way, for L equals P that captures the geometry in the same way here, we can think about, so now let's work over K again and say that we have an elliptic curve which extends to an elliptic curve over the ring of integers. So if it has good reduction, in that case, then if we look at the L to the n torsion we can think of the L to n torsion as now a scheme over OK. And so this is a finite flat commutative group scheme. Over OK. And so if you want, we can consider all finite flat commutative group schemes. So always commutative. And associated to any one of these guys, we get a Galois representation. So if you want, if I take one of these guys, then I just consider its k-bar points with the Galois action. But the fact that such a model exists, such a group scheme exists over OK, makes the representations we get very special. And so we're going to call the image of this map is the flat representations. So just to reiterate, if we have an elliptic curve with good reduction, then the L to the n torsion on that elliptic curve is a flat representation. So that's our motivation for why this is an interesting thing to consider. Can people see over here? OK. Oh, one more remark. So I'm going to also call, so this G, so G is then a finite, we'll call that a finite flat model for, so it's a finite net model for the representation. So in general, in this generality, this is sort of neither injective nor surjective. So then the flat deformation problem, so let's assume rho bar is flat. And then we want to study then deformations of rho bar, which are also flat. So this is the rho bar flat deformations. Without some without some thought, it's actually, I think, not totally clear that this is even like a subfunctor in a reasonable way. You have to sort of think about that. This is a somewhat subtle condition, but at least in the case but when L is not equal to P, this is something we already saw. So if L is not equal to P, then this flat deformation ring is just the unramified deformation ring. Okay, but then when L is equal to P, it's a much subtler question, and then this is the fact of so a result of Ravi Ramakrishna. So when L equals P, he showed that D flat rho bar is a local condition. So it's represented by a quotient R flat rho bar of R rho bar. He also showed that when K is QP and we're working with GL2, that this is in fact that R rho bar flat is formally smooth. It's actually a smooth It's actually a smooth deformation space. So this was his PhD thesis, which, if my chronology is correct, was he finished up just a couple months prior to the announcement of the Wiles' announcement of the proof of Fermat's last theorem. So yeah, he was a student of Wiles.
So you talk about G of K bar.
Yeah.
So that's a finite group. But when you in world of deformation theory.
Yeah.
GLN of some finite ring.
Yeah.
So what's the relation? So apparently that finite group is a module over that finite ring. And how do you sort of keep track of that when you formulate these deformation problems and you want to say flat deformation?
Right. So in terms of the formulation of the condition, we just sort of we ask, is it flat, forgetting the A module structure. Meaning we're not demanding that in the formulation of the condition, we're not demanding that A in fact act on the group scheme. Is that what you're like? If A is our coefficient ring, I mean we have A is an Artinian ring, so it's finite, right? So yeah, so we're not asking that. This will come up again in a second, but we're not asking that A in fact act on the group scheme. We just forget the A structure and then ask, is that finite representation flat? In the world of representations on finite, finite groups. Yeah, finite groups. Yeah, that's good. Okay. So from now on, we're going to take L equal to P. And so we would like to study this deformation problem in more this flat deformation problem in more general situations. And so the key technique, or one technique that was introduced, so L equals P, and then is what you might call sort of moduli. Goes by moduli of finite flat group scheme, or finite flat models maybe. It's the best way of describing it. So the idea here then is that so then this is a technique introduced by Mark Kisin, and so he proved that there exists a projective map, projective scheme over spec of R flat rho bar with the property that, so this is, call this theta, so that if we look at Artinian points, so if we look at over so maybe, yeah, I'll come back to your question in a second. So the fibers over it should be the set of finite flat models for the corresponding representation. So the rho sub x into GLN A. And let me just finish off with to finish the theorem, and then I'll say a bit more. It has the property that when you invert P, it's an isomorphism. So it's like sort of a resolution of the flat deformation ring. And so two remarks. The first one related to both related to your question. One is that one of the problems with constructing this guy is that, as you pointed out, unless the coefficient ring is finite, then this flat condition doesn't have any meaning. So in some sense, if you want to formulate, so that it only makes sense to the fiber here only makes sense when A is finite. And so, sort of formulating this is a bit of a, thinking about what a family of finite flat models ends up being is a bit tricky. And the reason I put the quotations here is that in this instance, one really does want finite flat models with an action in the coefficient ring. So the A should actually act on the. But that sort of, once you work over the generic fiber, that all gets fixed. And so the coefficients are automatic. It's automatic that the coefficients act. Okay. All right. So this resolution is most interesting when our field K is very ramified over QP. If K is unramified over QP, then in fact it's just an isomorphism. You don't get anything interesting. And the next remark is that the fact that this is an isomorphism, at the end of the day, comes down to the fact that the isomorphism follows from Tate's conjecture for p-divisible groups. So the fact that p-divisible there's some sort of unique integral model for a p-divisible group. So how does this help us? Theorem, yeah. No, theorem. Full faithfulness theorem. There's a lot of Tate conjectures. Right? Okay, so how does this help us? Well, one of the key questions we'd like to answer about these flat deformation rings are, and this comes out of the techniques involved in the proof of the modularity lifting theorems, is we want to know, I mean, you could ask many things, but in particular, you want to know what the connected components are of the generic fiber. And so because this is an isomorphism in the generic fiber, one can then convert the question about the connected components of this guy to some question about the geometry of this guy, which has a kind of moduli theoretic interpretation. And so I want to say I want to say what the to say exactly to say a bit more about this question. We first have to fix a discrete invariant. So if you look at the space of p-adic representations, the lifting row bar, which are in this generic fiber, then there's this there's this invariant that comes out of it, which I'm going to write as mu1 for mu g, and the mu sub I are they're n tuples, and in this case just contained in 0, 1. So this invariant is called the p-adic Hodge type. I'll say a few words about it in a second. But so then we're going to take the mu type to be the closure of connected components with type with p-adic Hodge type mu. So let me say, so what is this mu? So if we're just working with an elliptic curve, okay, TP E, all right, then our mu's would just be every. So this is two-dimensional. Then we're just all the mu I would be 0, 1. Okay, so this is somehow this p-adic Hodge type is the p-adic. It allows you to if you have some Galois representation coming from algebraic geometry, you basically see the Hodge numbers showing up in the p-adic representation. Alternatively, if you have a modular representation, then the mu would be related to the for example a Hilbert modular form, then you would be related to the weights of that Hilbert modular form. So that is, you can sort of pick out which component it would lie on. Oh. So the g is related to the way the coefficients act, because so in this case this representation is defined over QP, and so then you would sort of all the weights would be the same. Whereas if say you worked over if you TPE, but then you had some weird but say we had some other field F which was acting on it, then you would look at how the F decomposition relates to the sort of mu decomposition, and that's why you get the G different copies. So in fact, this is really only defined over over sort of the reflex field thing. Yeah. Yeah. Yeah, so this is like right. This is. Yeah, so this you could. Probably the right way to think about it is as a rigid analytic space. It's not the functions. Yeah. Of course. Sure. Right. This is right. But I think it's a result of de Jong that somehow these connected components are the same, whether you think of it this way or that way. So this gets used at some point. Yeah. Okay. So then what can we say? What do we know about this question? So using the Kisin's resolution, a series of work by a number of people, we're able to conclude that was able to answer this question when n equals 2. So if n equals 2, and for simplicity, I don't have to assume this, but just for simplicity of writing the theorem on the board, let's say rho bar is irreducible, then this space over P is connected. And so, and the way that Kisin's way the resolution gets used is the following result, which doesn't depend n or p, n doesn't depend on n. So for any n rho bar, the connected components of this guy are in bijection with something else. Oh, sorry, this should be rho bar. So it's in bijection with the connected components of something related to this x. So this is, now I'm running out of space. So this is the fiber over the close point of mu. So let's go back. So this is a complete local ring, and so we can so the fiber over the residue field is in some sense it's just some moduli space whose points are finite flat models of rho bar. So in particular now we have this x naught here. It's a projective scheme over a finite field, and it sort of only sees the finite flat models of rho bar. So it sort of only depends on that finite amount of data. And so what this theorem is deduced from studying this moduli space, which has a sort of linear algebra, in fact has a sort of linear algebra interpretation, and at least in the case when we're working with GL2, it's concrete enough that you can really get your hands on it and compute with it. Whereas this generic fiber is much more complicated. And so since my title of my talk mentioned local models, I should say that in order to conclude this result about connecting components, what we need to show is that the original x that we constructed, I should call this x flat, that this original x which we constructed is has nice singularities. And then we do that by showing that the singularities are the same thing, are related to the singularities of local models of Shimura varieties. How are we doing? Not bad. Maybe I think I'll write that, in fact. So so maybe the hard result that goes into this is showing that x flat mu so that the sort of local structure, so that in particular meaning mainly the sort of completed local rings of x flat mu are equivalent to the local structure of a local model for the group, the Weil restriction from K to QP of GLN. In particular, the special fiber of this guy is over ZP, or is reduced. Okay. All right, let me start with a fresh board, and then I want to say say something about my own work, which generalizes this construction of Kisin. So the setup is, now we start with an algebraic group, and let's fix a representation. So let's just, for simplicity, work over ZP, but any finite that's not necessary, and assume that this is connected reductive over ZP. And so you could think, for example, like symplectic group or orthogonal group or any sort of. And then let's fix a representation. Now let's have our row bar be valued in the FP points of our group. So now it can be some representation which fixes some polarization, for example. And then we can define the G-valued, say the G-flat deformation ring, deformation problem. And so what is that? So we're going to consider lifts of rho bar to G of A. Oh, this is A. Such that when we, so this flat condition was only makes sense for GLN, or valued representations, and so we say that the lifts whose composition with that faithful representation is flat. So, sure, yeah. Yeah, just to differentiate from what we were talking about earlier. And I should say that there are other ways of formulating this that sort of don't involve this fixing this representation, but and maybe I can talk about that if people have questions. Is that because a priori this notion of being flat, for example, is not preserved if you take the dual. So it would be it's very intrinsic to this representation. All right, and so again, this is no problem. This G-valued deformation problem is again represented. So this is represented by some what we may call or flat G rho bar. And one can do a similar construction. One can construct a G version of Kisin's resolution. So this is, again, projective. And you want to think about, you can sort of intuitively think about, though this is not quite right, that the fibers are finite flat models which have some additional, which are preserved by some additional structure, like a polarization or with additional structure. In the case of the symplectic group, you could really think about like finite flat models, which are whose Cartier dual is sort of self-dual. Okay, and so again, if we invert P, this is an isomorphism. And oh man, I could almost just leave this here. And so then the theorem is the analog of the connected components result so now our discrete, we're going to fix that discrete invariant, which is now going to be mu1 again for mu g, but now these mu sub I are co-characters of G of our group over geometric co-characters over QP bar, and for this to have any meaning, I should say say that these are minuscule. Then if sort of impose this condition of having p-adic Hodge type mu, if this is the then the connected components are going to be related to the connected components of the special fiber of this guy. Hodge type mu. Then the connected components of, what did I call it? 1 over P, okay, are in bijection with the connected components of the same thing, x flat mu g, the special, this is the fiber over the closed point. No, that's as a side comment, I should say that I mean, for some view, it is possible that both sides are empty. But it should mean for certain groups for some view that we're not. Back on. Yeah. So, I mean, so this is somehow not the right. This is somehow not the right formulation. We should really talk here. There should really be the G value, this crystalline deformation ring with Hodge p-adic Hodge type mu, not the flat. This flat condition is somehow. And then that's something that you can define independent of the embedding, and in certain cases those would coincide. I mean, at least sort of mod p torsion, they would coincide. Is a crystalline deformation is constructed as a flat, as a sort of quotient.
In the original setup, where you start with the representation for GLN.
Yeah.
If you compose with some representation of GLN and some GLM,
then it's not going to be flat. Yeah, so I mean, in general, if you take the tensor product of two flat representations, that's not going to be flat. If you take the dual, then normally you. So I mean, at least so for example, if we're talking about ZP representations, in the torsion-free setting, then this flat deformations, which would mean coming from a p-divisible group, correspond to Hodge Tate weight 0, 1. So you take the dual of that, that's going to be Hodge Tate weight minus 1, 0. And so you're already, unless you happen to be, unless you happen to be in a very special situation, normally that doesn't happen. And that's kind of one part of the problem. That's sort of the difficulty the main difficulty that goes into this theorem is somehow when you start taking tensor products of flat deformations, you lose some of the finer control that Kisin had. So I think I should have time to say something about that. I can, after the talk, I can say a little bit more about. I do use something like this in my technique, but I don't think it's necessary. So I should be able to remove that. So I did want to say as an interesting corollary that if K is unramified over QP, then I told you that, or maybe I'm not sure I mentioned it, but in the GLN case, it's known that if K is unramified over QP, then the flat deformation ring is smooth, formally smooth. And so the same thing then is true for the G value. So then R flat mu sub G is formally smooth. So that's with no, for any G. And I should say that corollary of the theorem, though with a little more input, but the main content would be somehow that, well, or maybe they're both corollaries of the fact that the local structure of this guy is, we understand the local structure, and in the case when it's unramified over QP, you can show that that thing is in fact. No. I should say that, no. The corollary of the method. No. And I should say previous work on this. So Michael Broshi, a student of Kisin, studied the just sort of the GSP2G case, and formulated some general stuff for G as well, but the end result was only for G. Okay, so I want to say a few words about the sort of technique, the theory that goes into this. So to do that, let me begin by just for simplicity. So I want to say a word. I have to say a word about how do we construct this map theta. So let's assume for simplicity that K over QP is totally ramified, just saves notation. And fix a uniformizer of K, uniformizer, and so this X, this X that we've constructed, it's a moduli space. But we're not going to work with the finite flat group schemes themselves. So what we're going to work with is something which comes out of maybe integral p-adic Hodge theory. So if we work with finite flat group schemes that are killed by some power of p over OK, then there's a description of these guys in terms of torsion sigma modules. So these have a sort of linear algebra description, and that's what we actually work with. So what is, I won't be able to say too much about this, but so this sigma is a ring, it's a power series ring in one variable over ZP. And so we're looking at, and it's got a Frobenius So it's got a Frobenius, which sends u to u to the p. And so what are these sigma modules? Well, it's a module, so it's a sigma module, which the Frobenius so this is which is a Frobenius, which is semi-linear with respect to that Frobenius. Semi-linear. And then this height condition is the fact that the is this kind of funny condition, which is that the module, the image of Frobenius is contained in E of u times m, where, stop for a second. It's contains. Yeah. So it's semi-linear, so I take the module generated by the image. And it should be contained in this, should contain this E, sorry, yeah, I misspoke. And this E of u is the minimal polynomial for pi over qp. Yeah?
Next to E of u that you wrote.
This m. So.
You're assuming k is totally ramified over qp.
Yeah, just so to avoid some extra notation. Yeah.
Pi is a uniformizer.
And pi is the uniformizer of OK.
And version means killed by the power of p or killed
Yeah, so it should be, yeah, it's a little more, it's, right, it's killed by a power of p, but then you also, you don't want it to be u torsion, you want u torsion free as well. So there's some slight subtle condition, but killed by a power of p, that's what we mean by torsion. Okay. I was going to say something. Right. And so, so we work with these guys, and then if you want to impose some extra structure, for example, preserves of polarization, or say something about the, if you take its n-fold tensor product, it has some extra, has some extra structure on it. Then what happens is this: as soon as you take a tensor product of these two guys, this height condition, you move outside the height less than or equal to 1 condition. So, and this becomes, that this contains maybe some power of E of u or something like that. And so, and the problem is that there's something kind of special about this height less than or equal to 1 situation. So when, so outside of height less than or equal to 1, somehow you lose the Kisin module the sigma module, well, sometimes also called Kisin modules. So, but since I've already said Kisin enough in this talk, sigma module captures the Galois action of only a subgroup of the Galois group. So it's this Galois group over k infinity. So k infinity is where we enjoin a bunch of powers, pth roots of the uniformizer. Like in Unisawa theory, except we're using this non-Galois extension. So this sigma modules is like for this non-Galois extension is kind of an analog of phi gamma modules for the cyclotomic extension. So there's kind of a relationship there. Or maybe the next thing is more of an even better relationship, which is, so what I use in my theorem is that there's a sort of souped up version of this this theory, which does capture the full Galois action even outside of even beyond this height less than or equal to 1. So Tong Liu is this theory of what I call phi gamma hat modules. So he uses G hat, but to avoid confusion with the group G, so phi G hat modules. So we use Liu's this version, which allows me to identify sort of the local structure. I'm being a little vague here, but local structure of x flat mu g. Yeah. It's join all the p power. I kind of trailed off, but you make some choice of pth roots all the way up to p power roots of the uniformizer. Yeah. So let me also say, just to be able to, right. So Kisin's in the original work on GLN. So he constructed this moduli space, which is a moduli space. Really, this is a moduli space of sigma modules. So in my situation, we want some analog of sigma modules, which would have this G structure. And so I want to just give the definition for people to think about. So, because this is sort of, so, yeah. So what is the resolution in this case? So what it is some sort of moduli space, and what's the moduli space? Maybe the most natural way to set it up is that we have now a G bundle P over the sigma, this ring sigma. Or maybe I should say sort of if we're working over our Artinian ring, it should be sort of over sigma tensor A. Let's just be clear. So sigma tensor A over ZP. And then we want the analog of the Frobenius is I take I pull back this bundle by Frobenius, and then I want to give you, and then I want to invert E of U, and then I'm going to give you an isomorphism with the same thing. E of U inverted. And so this sort of condition, this fact that we're inverting E of U, kind of it sort of captures the fact that if you give me any representation of G, and I consider I can take this bundle and I can push it out to get a vector bundle, then that vector bundle will be equipped with a Frobenius, which has finite height, though that height may vary depending on the representation. Okay, and so I guess my remark is that this x flat G is a moduli space of such things. G structure. And the last thing is that the local structure of x flat mu g is then related to it's related to a local model for the group Bay restriction K of QP of G and this co-character mu, and the definition of such a local model is related to so local models were only recently defined for sort of in this generality, and that's due to Papas and Zhu. Right, so this is local model in the sense of Papas Zhu. Okay, so I think I'll call it a day. And if you have any questions, anyone have any questions?